Okay, so it's my great pleasure to introduce Krzysztof Burdzy, who, of course, many of you already know as the kind policeman for the open questions session, but maybe some things that you don't know as much about him as he has contributed immensely to the probability community. Received the 2016 INS Carver Medal for curating and co-founding the Electronic Journal of Probability. We saw people, citing papers from EJP, Gregory's talk, with sustained vigilance to give open access to journals, and also help lead the seminar on stochastic processes and then police the open problem question there. In terms of, he's a Rothschild professor now here, so he'll be here for a bit longer, that you can avail of his presence here. And he has done, of course, phenomenal contributions to stochastic analysis, ranging from nonlinear PDEs inspired by billiards, Archimedes principles, about which he'll give a public lecture next week, even some things about SPDEs, and of course, reflected processes, including stable sensor processes, counterexample to the hotspots conjecture, and Markovian couplings, and now we will be talking about reflected value. Thank you.
Okay, well, thank you very much, Kavita. Now you put a lot of stress on me now, because if I make any mistakes or whatever, okay. So let me say, I'm really grateful to the organizers for inviting me to this workshop, and also for inviting me to the program, because I'm staying here for the whole month. So it's a great pleasure and a great honor to be here. Well, the title of my talk is exactly like the title of my paper with Rich Bass. It's a preprint at this point. And Rami told me that my talk will be trivial. He said that on Monday. He said that if anybody is working on reflected Brownian motion in the first quadrant, that's a trivial model. So don't worry, Rami, we are still friends. Okay, so here it is, reflected Brownian motion in the first quadrant. Obliquely reflected, there are two angles, θ1 and θ2. They are constant on each side. The convention is that if the angle points towards the origin, it's positive. The equation, the Skorokhod equation, is driven by Brownian motion, and we have the local time push on each side. And the relationship between the angle and AI is that A1 and A2 are tangents of the angles. So, okay, so this is a historical review of some results, and I'm glad that experts like Kavita and Ruth are here. So if anything is wrong, please correct me right now rather than criticize later. So I believe that weak existence and uniqueness in law is known when θ1 plus θ2 is less than pi/2. And for those of you who are not very much familiar with this condition, I believe that the equality is when the two vectors point at each other, right? So that's like the critical case, right? If you're not familiar with this. Okay, so I read my own sentence, and okay, it says something about making sense. I think that the sentence doesn't make sense. I think I should have said simply that ORIB-MEM, obliquely reflected Brownian motion, is a semi-martingale if and only if θ1 plus θ2 is less than pi/2, and let's ignore the rest of the sentence. I think that the first part of the sentence actually is correct, right? Okay. Now, pathwise existence and uniqueness is known if A1, A2 is less than 1. But it is also known in some cases when A1, A2 in absolute value is greater than 1, right? Is it true? Not in 2D. So in 2D, this is the best there is at this point, right? Okay. Okay. And the last remark is this. and equal to 1. Okay. In what? In okay. And the last remark is that when theta1 plus theta2 is less or equal to 0, then the process is transient and leaves the origin forever. Well, still the question of pathwise, or anyhow, existence and uniqueness still makes sense if you start at the origin. But somehow we are ignoring this in our work. So we are interested in the case when the process keeps coming back to the origin. Yeah, it's a yeah, transients. I believe this is if and only if condition. Oh, because it can come back to a neighborhood. That's what you mean. Yeah. So for transient it would be less, right? Yeah. Sorry. Okay.
Not when theta is less than equal to 0. It's either null recurrent or transient. And if it's strictly less than 0, then it doesn't come back. Yeah. Less than or equal to it doesn't. That's like Brownian motion. Yeah.
Like Brownian motion, yeah. Okay. So I believe that this is the first result on pathwise non-uniqueness, as far as I know. So that historical review was, I hope, helpful, because now you understand all these conditions. You should understand all these conditions on the first line. So these conditions are sort of natural. So first of all, we want theta1 plus theta2 less than pi over 2, so that we have semi-martingale. Then the conditions on theta2 and theta1 are such that actually the process has a tendency to go to 0, so it will return to 0 infinitely often. A1, A2, the product, that the absolute value is greater than 1, because if it's less than 1, then we have pathwise uniqueness. So it's a natural. So really the only new condition is, like, the significant condition is this. And and we claim that pathwise uniqueness fails for this equation. Okay, so I just want to give you an idea about that condition, what it does, the kind of restriction that imposes on the parameters. I will not explain it, but it is natural that I restrict theta1 to the values between pi over 4 to pi over 2, and the other parameter goes from negative pi over 2 to 0, and the yellow region is where pathwise non-uniqueness result holds. But we don't know what's outside. It's not, it's not our condition is sufficient, but it is. And actually, at this point, I really don't have a very good guess what's in the rest of that blue region. So that's an open question. Okay. So this is the only theorem that I'm going to present today, and let me tell you what I'm going to do next. So first, I will start with a historical review of counterexamples of non-uniqueness, examples when the driving function is deterministic. And then I will discuss our proof. And so that historical review will play the double role. First of all, I want to review what we know already. And second, this will help me to explain what we've done by comparing it to what is already known. Okay, so the first counterexample, or the first example of non-uniqueness, was invented by Avi Mandelbaum. The paper was never published, and Avi said that this is one of his best cited papers. So if you know about this paper, or if you have a copy, then you're like in the in group. Well, okay, so this was an example. And you see, this picture is helpful if you want to understand what he did, but it is not helpful for us, not today. So I will have better pictures, but I wanted to show you his picture. Okay, it's a better picture, and as far as I know, this was the first published example of non-uniqueness from Bernard and El-Karoubi. It's a three-dimensional example, but from the point of view of today's talk, the picture is good enough. I will be working in 2 dimensions, but that's good enough. And I claim that actually Mandelbaum's example is published in a sense. You see, Whitley was Ruth's student, and the way I interpret the laws is that if a PhD thesis is submitted at the university, then the university places a copy of that thesis at its library, and then it's published because you can go to the library and read it. So the example is published. So Whitley included it in her thesis. Yeah?
And it was just, she didn't really invent this picture. She was just recounting the story.
Yeah. So, I mean, she wrote Mandelbaum's example, so she did not claim that it was her example. She was clear about this. Okay, so I want to talk about the last 2 pictures now. So you see a little bit of a pattern here. You see this zigzag pattern. So this zigzag pattern, left, right, and so on. And here's another pattern that goes like this. This is some kind of a spiral. And so I will draw a number of pictures trying to explain how the Avi's example worked. So the idea is this: you want to have not just, because here you just see one path, but you actually want to see 2 paths that are synchronized. And let's call it a cycle. This is, like a coil in the spiral, or a cycle. And the example, Avi's example actually is not that simple. This is in the sense that it's not so nice. It's not a spiral. It's sort of some kind of funny example, whatever. But the point is that it's very simple. One cycle consists of only a finite number, like 4 line segments. And that's all. So the example is real simple in the sense that both cycles are very simple, but it has to be clever, because you have those fixed angles of reflection. You have one driving function, and that one driving function has produced the effect that after one cycle, so let's say we start here, we go up, and here, right? You end at a point that is on the same half line, same ray from the origin, but at a greater distance. And that stretch has to be the same for both solutions. The reason is that what you can do is then you can rescale. So this is a bit like what do they call it? For fractals, self-similar construction, right? So basically you rescale, and after rescaling, everything fits together because the 2 new endpoints fit with the old endpoints. So in the end, what you will have is 2 spirals, and we naturally try to think about, going forward, right? So there will be this, oops. So the solutions will be, farther and farther from the origin, but actually from the point of view of the example is the opposite. What is crucial is that we can make, smaller and smaller coils, and they will meet at the same point at the same time. And this is the point where you have non-uniqueness, because then you look forward from that point in space-time, and you see that you get two solutions that sort of immediately make that infinite number they have infinite number of oscillations or loops, right? And this is how it works. So, so as I say, this picture comes from a paper of Bernard and Al-Karabi. Mandelbrot's picture is of the same kind, right? I mean, there's this self-similarity, except that I say his building block was less elegant. Okay, so now what I want to do is I want to in those examples, there were two, but I believe that, let's see, I think in Bernard and Al-Karabi, it could be three, right? Because I think that there was this.
I mean, also if you do different driving functions, if you would just do a linear, because sometimes you can make it stick at the origin and then move. So then you could stick any amount of time at the origin.
Okay, so now what I want to do for the rest of my talk, I want to explain to you how our example was constructed. And what I'm going to do is, in some sense, I will tell you how our example has to modify Mandelbrot's example. So this is the construction of just one cycle, right? Because we started with just one cycle. So X and Y are two solutions driven by Brownian motion. And suppose that we are away from the origin. So we are somewhere here. And so Y and X are reflected Brownian motions. And suppose that X and Y reflect only from the horizontal axis for some time. Then it's very easy to see what's going to happen. After some time, so first of all, X will be reflecting first, and then Y will hit the axis. And it's very easy to see that the distance between X and Y will be stretched by the factor of A1. Strictly speaking, absolute value of A1, but in this case, that's the positive, okay? So that's elementary calculation. So we get that stretch. Then, Brownian motion will take these particles, X and Y, somewhere else, and well, they will start reflecting at some point from the vertical axis. And once again, let's assume that for some time they will be reflecting only from the vertical axis. And then once again, it is easy to see that at some point Y will get to the axis, and then X will be pushed in such a way that the ratio of the distances is the absolute value of A2. And this is why we get A1 times A2. That was this condition. Well, in absolute value, right? So AY times A2 after, Now, this is actually half cycle. I just wonder if you've noticed that Y is at the top here and X is at the bottom. X is at the top, Y is at the bottom. But if we repeat that, then after the full cycle, you will have Y at the top, X at the bottom. So that's the idea. Okay. So there is a number of problems. This will not work just like Abi's example, because his example, recall, was based on the idea that we take that pattern and rescale it to make it smaller and smaller and smaller and smaller. And finally, we will get to a point. And then at that point, we go back and we have two solutions. I cannot do that. And but I said we cannot. We cannot actually means Rich, Bass, and me. It's not in the general sense. We like humanity. No. The point is this. We are dealing with Brownian motion. So obviously, I mean, nothing can be repeated exactly like in the deterministic case. The only question is whether you can repeat the pattern, right? The general scheme, not the actual path. But if I go forward in time, I just use the strong Markov property, and whatever I was able to prove for one cycle, I can prove for the next cycle. Going back in time presents problems. You see, obliquely reflected Brownian motion is a Markov process, strong Markov process, as long as you're away from the origin, no problem. But reversing time changes the problem. It changes the process. And I don't know how to handle that. So one can write some formulas and so on, but I wouldn't know how to rescale and add those smaller cycles. Yeah. I am assuming that A1 times A2 in absolute value is greater than 1. So our scheme will be different. Namely, what we are going to do is we are going to start two solutions very close to 0. Show that they diverge. And then we will start closer and closer to 0. And in the limit, in the appropriate limit, the two solutions will start actually at the origin, and we will have two diverging solutions. So it's a different scheme. It's not that easy. I mean, we have to go through some limiting process to get a counterexample. Okay, so when I presented the idea, I said, well, imagine that X and Y interact only with the horizontal axis for some time. Okay, this can happen, but look, this is Brownian motion. So if you see distances that are here, it's absolutely clear that these Brownian motions, or these reflected Brownian motions, driven by Brownian motion, can easily go to the other side, right? So X may start reflecting on the horizontal axis, then vertical axis, then horizontal, and so on. So there's this separation that first we reflect on the horizontal, then we reflect on I mean, this will not work unless so the real picture is like this. So I am not suggesting that this is a point where there is non-uniqueness. What I'm suggesting is that visually, the two paths most of the time will be so close that if you look at them, you will see just one path. In the sense that the distance between two solutions over here, compared to the distance, right? So there are two solutions here, and there's the distance from the origin. This distance is so small that for all practical purposes, this is just one path. But then it is much more believable that when you have reflections, then both processes will reflect on one side, then they will reflect on the other side, and again on one side and the other side. And this is something we have to prove, that basically it will never happen that X, well, never, for a very long time, it will not happen that X reflects on the horizontal axis and then vertical and so on. No, both processes reflect on one side and then the other on one part of the boundary than the other part of the boundary because they are so close. So for all practical purposes, this is just one process. Okay, I call it challenge because this has to be proved, right? I mean, that it's like an element of the proof. You have to prove that. Okay, the process has the wrong drift. So I wonder if you've noticed, but I don't know if I stressed that, but our drift actually pushes the process towards the origin. That's the assumption on our drift. Because there are two angles, and the angles that, you know, is directed to where the origin is, that angle is greater. So the process has a tendency to go to zero. But, you know, sort of intuitively, I mean, this process should go away from zero because we want two paths to go apart, right? To separate. So they will not separate if they go to zero. So what really it means is that we have to look at an excursion. Because if you have an excursion, right, so it's a part of the trajectory, then actually the process has a tendency to go away from zero, right? Because it has just visited the origin, and along the excursion, it will go away. So this gives me an opportunity to introduce like an aspect of our techniques that we use. So it turns out that to do some calculations and arguments and so on, it was convenient to use 3 different representations of this process. So the original one is on the left. And then what you can do is you can use a conformal mapping to change the angles. Oops. Over here. So you map conformally the wedge into a different wedge. And in that different wedge, the reflection vectors point against each other. And this gives us a very sort of convenient way of thinking about this. You see, in this picture, the vertical component of the reflected Brownian motion is just Brownian motion reflected at 0 because it cannot go below 0. But there is no local time that would affect that vertical component. So for example, if we say that we look for an excursion of this process that hits this line, for the vertical component, this is just an excursion of Brownian motion from 0 to y. And we know the distribution of this process, this is Bessel 3, 3-dimensional Bessel. So you see, so in this way, we have a process that has the drift in the direction that we want, away from the origin. And finally, I just wanted to show you that we worked actually quite a lot with this picture. So this is the logarithmic transformation, because for some computations, it was just the easiest case. Yeah.
In the first picture, you have the first picture, particles moved parallel before they hit. But in the second picture, do they have same noise, or you have some nonlinear sigmas?
Okay. Please wait like a few minutes, and I will have a slide on that. Okay, the next challenge, there will be 2, but one of them is probably the first challenge is more relevant and more important. Okay, so I'm constructing a process that, you know, that my picture suggested that there is some process going over here. So now let's draw the same path, but going backwards. Okay, so what the picture is suggesting, it's supposed to suggest is the following. Going forward in time, the 2 paths Okay, so at this point, I will have visible two paths or visible separation, right? Which means that if I go back in time, they will be closer and closer relative to the distance 0. But this picture suggests that actually the two paths will not be close enough. Well, there are two things that we have to balance. One is the rate at which paths either separate in the forward direction or get closer and closer in the backward direction of time. And there's the other thing that I have to account for, namely the drift. Because the process goes, on the logarithmic scale, it goes like one block at a time, right? It has a drift. And the question is how the two match. So that condition, you remember there was like a new condition that I displayed. This is like the only new condition, because we have the two rates to match, so that actually it's true that the two paths are close to each other, or much closer to each other when they are close to the origin. So think about this. If we are here at the distance, something like 2 to minus n, when n is very, very large, then here the separation should be like 3 to negative n, right? And the two, the numbers 3 and 2, we obtained them from some estimates. Okay, so this is one challenge. The other is sort of less interesting. You see, we have to prove a law of large numbers, actually a strong law of large numbers, because as I say, there's a certain tendency and there's a certain rate. But what this translates into is some kind of law of large numbers. But we don't have independence here in those blocks, right? Well, whatever Brownian motion does in one block affects the other. So, we used a paper by Russ Lyons from '88. And the thing is this, we don't want to prove like a new ergodic theorem. The only question is to find the result that is already, right, an off-the-shelf result, so that you can verify the assumptions in the simplest way. So I'm not claiming that Lyons 88 is the best. Probably we can find a better way of doing this, meaning find a different theorem that will give us the same estimate, but it will be easier to verify the assumptions. But this is not a very interesting challenge because, dependence, I mean, for the sums is like not a very interesting thing. Okay, so Andre, I believe that this may address your concern. So this is something I swept under the rug. When you do conformal mappings, you can only conformally map one process at a time. You see, people say that Brownian motion is conformally invariant. This is just plain false. Brownian motion is not conformally invariant. You have to change the clock to get Brownian motion. And if you have two processes driven by the same Brownian motion, if they are different, so they are in different parts of the space, the clocks will be different. So there's no way to time change both processes so that they run at the same time, right? And somehow something will be desynchronized, right? Like that they will be at the corresponding points at different times. So the way so that was another challenge. So what we did is the following. We worked only with one process, because for one process, there's no problem. I mean, you map the Brownian motion, you time change, you have Brownian motion. Then we proved some properties for just one Brownian motion. And then we claimed that as long as the other reflected Brownian motion is close enough, then we can prove some things that we need to prove. So it was like we circumvented this problem. But at least, well, you cannot time change both Brownian motions at the same time. Okay. Now,
so you said as long as the other Brownian motion is close enough, but you're trying to show that it's going apart.
That's right.
So
that's right. So now, I believe this is the slide that will answer your question. So I guess this picture will be very much like perhaps my first picture, or one of the first pictures. So first of all, we have just one path, and then we have two paths. And of course, this is an idealized representation that the two paths are very, very, very close. And then some point they are far apart. So from the point of well, I have to have two paths far apart because in the limit, I want to prove that there are two solutions. So I fix some time, say time 1, or the distance 1 from 0, right? And I claim that at that time, or at the time when the process is 1 unit away from the origin, I will see actually two solutions on that scale. So this is visible, right, on scale 1. So maybe the distance is 1/2 or 1/10. It couldn't be 100, but it has to be comparable, so that in the limit I see actually the separation. Okay, so recall that our scheme says that we are starting closer and closer to the origin, and that n refers to the logarithmic scale. So this is why you see the strip here and not the wedge. So think about this point as 2 to negative n units away from the origin. So after taking logs, what we get is n. And here we have a problem, because we will have the law of large numbers, meaning that if we go through every block, something is going to happen. The processes will go in a certain direction. Their distance will change by a certain number, and so on and so on. Unfortunately, there's the central limit theorem, which spoils things. Why? Suppose that we choose our starting point, and we are very smart, and we choose that we put two initial positions at the right place, and then the process keeps going. And unfortunately, I cannot guarantee that it will be at distance, say, 1, and the separation will be here of order, well, let's put it like 1/4 or something. Why? Because we have square root of n, which means that, yes, you will see the separation, but on the scale, since I use 2 here, it would be 2 to power negative root n, or 2 to power root n. That's because of the central limit theorem. And this is not good, because if you see the separation on the scale 2 to power root n, that when n goes to infinity, this goes to infinity, and you will not see the separation in the limit. If the separation is on the scale of 2 to negative root n, you may say, okay, so it separates quickly. Yes, but it separates so quickly that I don't know what's going to happen next. Yep, it will separate very closer and closer to origin, and I'm back in my original problem, because then I have somehow to claim that we have two solutions. But what? That was the original problem, how to prove that there are two solutions starting from 0. So what this is the most, I would say, subtle and suspect, but I'm not sure about subtle. You have to tell me whether it's subtle, but it's certainly the most suspect part of the proof. Namely, I have to look into the future. So what we do is we generate just one path. No problem. As long as the path does not hit the origin, there's no problem with existence and uniqueness. So we just generate one path. There's one path of Brownian motion, one path of reflected Brownian motion. Then I inspect that path, that one path. Then I have information on the path on this whole interval. And then I go back to this point, and I choose another point, another starting point, so that everything will work, as I want along the path, and they will separate at 1/4. The separation here is, Here, in this case, it would be linear rate, and here like exponential rate. But I have to make sure that this will be at the right time. So this is as I said, the suspect part of the proof. But it depends how you think about this. The way I think about this is this. What we can produce, and if you forget about filtrations, measurability, and so on, what we can produce is, for almost every Brownian path, we can produce two solutions to the Skor-Hod equation. I mean, if you just look at the equation and forget all the measurability, adaptedness, and so on, you will see two solutions. So that much is easy to see, meaning that it follows immediately from the proof. But then, when it comes to questions like of strong uniqueness, strong existence, and so on, things become more subtle. And so this is why I called it subtle.
So
but-
just to clarify, this could still be strongly unique. Are you saying that
Actually, we prove in our
that you
paper
you
that,
say no,
that,
right?
that there's no strong
Yeah.
existence,
Right.
because once you have weak uniqueness
Yeah, and then
and weak existence and uniqueness, then strong existence and uniqueness go together, and we prove that it's not. But this is the part where I say it's subtle. So if somebody tells me that there's an error in that part, I will not be that surprised. We think that we were able to do that, but that's the part that is not obvious.
What you're trying to do, you're trying to construct alternatively a class of driving paths, which are discontinuity points for the forward map. Is that correct? And then when you feed it into the equation, you get non-uniqueness. Is that what you're trying to do?
Did you say discontinuities for the Skor-Hod map?
Yeah.
Okay, so to be honest, this is not the language where I think about. I mean, what we are constructing is for almost every Brownian path, we construct two solutions to the Skor-Hod equation. We claim that pathwise, if you fix a Brownian path, that actually you get, like a, because it's a deterministic question, right? If you fix a Brownian path, you have Skor-Hod equation, and the question is whether it is satisfied. And yes, you have two solutions.
Okay, so you are proving that path by path uniqueness doesn't hold.
Yeah.
Not pathwise uniqueness only. These are different.
Okay, so that's the subtle point. Yeah, but I guess
okay,
the way you put it, yes, path by path uniqueness fails for almost every Brownian path.
so it's a. Is it linked? Wait, what's the role of Brownian motion here? It seems what you're saying is a pathwise result.
Yeah, but
Is
pathwise
there
results, pathwise non-uniqueness was already proved by Mandelbaum.
so the thing is
So
that
there was already an example.
so the thing is, in the scorecard map, of course, you can take linear trajectories and they can be non-unique. Like, you can have two. So that's not surprising. But it turns out that you have, the key thing is that they prove that you have weak uniqueness. So the thing is that if you put a Brownian path, in law, they're the same. So then the question is, okay, if you're allowed to choose very regular paths, you can show that there is non-uniqueness. Can you also ensure there's non-uniqueness for Brownian paths? And that's
Which there is pathwise non-uniqueness. This is all the result. So what you're showing is that that set of paths is fat enough to have Wiener measure 1.
Yeah.
Okay.
Yes.
Yeah, I understand. But it's a pathwise construction. And the argument comes at the end.
Well, pathwise construction, I wouldn't use this because there's so much probability in our proof that
yeah,
calling a pathwise construction is just
yeah,
it's
it's not.
okay. So I'm going to finish with a curious observation. At a certain point, we had to calculate something, and after long and painful calculation, we got this formula, and my heart sank. Okay, this is a perfectly explicit formula, right? that, yeah. And, you know, there are theorems that have very awful formulas in the statement, but they're not nice. Well, it turns out that it simplifies. So if you can, well, I don't know if you want to spend time on this, but if you teach calculus or something, you may want to give it to your students. But there's like an extra story about this. You see, I knew about the simpler version to start with. So because otherwise I would just give up at this point. I wouldn't even try to simplify it. But since I already knew that it should be simple, I tried to simplify it, and I was able to. You see, originally we proved the simple version using an argument that I liked, but it was Rich who pointed out to me that the argument was totally wrong. So I have a feeling that there may be a good argument that we are missing that will give us immediately and easily this simple formula without going through some absolutely awful calculations. So who knows? Maybe it's, you know, it's like an open problem. I don't want to, if you want to spend time on this, but my point is that, you know, who knows, maybe our paper is suboptimal in this sense that we are missing an easier way of proving this. The final formula, our original idea didn't work, and we had to go through some rather complicated computation. Well, thank you very much for your attention.
Are there any further questions? If not, I have one. So clearly, like you said, there's another whole regime where we don't know, but at least here you have an example of pathwise non-uniqueness. And is this example generalizable even if under suboptimal conditions or something? I know you used conformal maps here, so you know it's not clear at all that you can do this in higher dimensions. But let's say even in 3, one would expect you still have pathwise non-uniqueness, at least in, or path by path non-uniqueness, however you want to say it, for Brownian paths.
So your question is about higher dimensions.
Yeah. Is there any hope? I mean,
Okay,
because you're using very
so
strongly
so the
conformal.
result of your question is that the open problem session tomorrow will be canceled because that was my problem. But let me elaborate on this a little bit. You see, there are 2 questions here. One question is actually on the technical side, whether one can adjust the techniques.
Yeah.
But my first question would be even to state a conjecture, because you see, okay, if we can go to, how about if you see in this case, the whole argument is based actually on a 2-point interactions, let's call it this way. Something happens on one axis, then something happens on the other axis. And this is a rather easy scheme.
But that's for one Brownian motion, and you need to.
Still, most of the time they travel together.
Okay.
So this is really one side, the other side. So you have 2 points. If you go to 3 dimensions, there is, or higher dimensions, there's no way you could have simply a switch between 1 and 2 and 1 and 2. It becomes immediately more complicated. So I would say even formulating a conjecture in 3 dimensions would be already interesting.
No, but I think that if you, once you have non-uniqueness in dimension 2, say for the orthant in dimension 2, automatically you have non-uniqueness in dimension 3. Simply start away from the origin.
Yes. But I'm thinking about the case when you, for example, have a cone in 3 dimensions, and the base is, say, a smooth function, and the vector of reflection is constant along the rays. And then, but there's no way you can reduce it to 2 dimensions because the boundary is smooth most of the time, and say that the angle of reflection is, or whatever, the vector of reflection is smooth. So you're totally right that in some cases, yes, it just it goes back right to the 2-dimensional case.
So is it important to you to have a truly 2-dimensional Brownian motion if you had just a covariance of rank 1, like in Sandro's talk? Could you have similar construction, or Do you need to have a,
If what again?
if the covariance had a rank 1, I mean,
Okay, so I didn't think about this. The thing is that our argument is based to large extent and fundamentally on some explicit calculations. So any even simple modification of Brownian motion would require like a new set of equations. You add some drift, or the covariance matrix is slightly different. It's possible that one can do them, but I cannot guarantee them because there are many places where we really relied on some formulas that I know for Brownian motion. And I'm sure that many of them can be generalized, but it would be it could be a much harder. So specifically in this case, I don't know.
Describe in physical terms the set of trajectories that has a probability 1 for which you prove non-uniqueness. What sort of conditions? What you involve?
You're asking about the driving paths?
Well, as
The
far as
Brownian paths?
yes.
The driving paths. But our result is, with probability 1.
Yes, that's
I think, if I may paraphrase, I think you're asking about some intuition into this condition, this tan theta 1. Of course, you said it's this balance condition. Am I right? That you're
yes.
asking about what is the physical intuition behind this tan theta 1 condition that you have, which leads to pathwise uniqueness. But of course, the first thing is it's
Yeah.
only sufficient, so you don't know that it's
But
necessary,
but
so
this-
it may not have any physical intuition.
This is not about properties of paths.
No,
This
no,
is the
no, but I think
properties
is that
of,
what you-
of the angles or vectors of reflection.
Right.
So the idea, recall, was that we get that stretching. You reflect, reflect, and the distance will be stretched, right? So it's like in Mandelbaum example, you get stretching over every coil, right? Or every cycle. So theta 1 and theta 2 have to be chosen so that every time there will be the stretch. And then the other condition was that somehow the process is not pushed at a certain rate, because that would not allow for that to happen. So you have to, there are two things, right? So first of all, the rate of stretching, and then the rate of, just escape from zero, and they have somehow to match. But this has nothing to do with Brownian paths. It has everything to do with the angles of reflection.
So yeah, I don't know if this has any relevance, but I guess physically sometimes when you bounce balls bouncing against walls, they actually become more synchronous after they've bounced against the wall. I mean, do you see this in your maths? Basically, that you have some two paths that are closer together, but are they closer together at the wall or just after the wall? Or is that nonsensical?
So I guess your question, okay, if I understand correctly, is related to that product of A1, A2 in absolute value. If it's less than 1, then somehow the paths are pushed closer and closer together. And what we are saying here, that at least in some cases, A1, A2 in absolute value greater than 1, that the paths are pushed away. And the bouncing, well, from my perspective, bouncing from the walls only applies that A1, A2. It's no more than that. Every time you have to multiply by A1, multiply by A2.
Are there any other further questions or comments? Okay, if not, let's thank Chris once again.